In this video, I'm just going to talk you through the atomic structure marked task 2. So question 1 says, Figure 1 shows a label from a box containing radium-226. Radium-226 emits alpha, beta and gamma radiation. And you've got the source here. This is radioactive source, this is the label. Radium with a 226, which is the number of protons and neutrons. And it tells you it emits alpha, beta and gamma. Handle only with forceps and always direct open end away from person. It then goes into question part A, which is figure 2, which is this graph here, the half-life graph, shows how the activity of radium-226 will change. It wants you to determine the half-life of radium-226 and wants you to show you're working on figure 2. So the first step in doing this, you need to zoom in and read the graph, okay? So, hopefully you've got this on paper, it'll be easy to see. I'm just going to zoom in here so you can see the graph. 1 second. I'm using the wrong thing here. That's the one. So we zoom in here. As I zoom in, you can see that where it intersects the line is just above 180,000. You see that intersection there? So it's a small square above that. So what I need to do now is I need to work out the value that will be on that small square. So we can see the difference between 200,000 and 180,000 is 20,000. Okay, and we know that we're having that going up in 5s because there's 5 squares here. So if you do 20,000, let's put this my work in here, 20,000 over 5, that will tell us how much each small square is. So 20,000 over 5 will give us 4,000. So which means that when we read this value here, it will be 184,000. So that's where we start at. 184,000 is our starting point. So now what we can do is zoom the graph back down, hopefully. Zoom back out of it. I can show our work in here. So you've got 184,000 is the top part. We want to know how long it takes for it to half. So I'm going to show you my working over here. I might make my pen slightly bigger. So we now know that we've got 100. Oh, it's probably too big. Sorry about that. Make it a bit smaller. So we know that we've got 184,000. And we want to know how long that takes to half. So we do that divided by 2. And you can always do that on a calculator, or you could do it in your head, and that comes out to be 92,000 becquerels, which we'll have left. So now what we want to do is we want to zoom in on the 92,000 becquerels and read across for the axis. So I'm just going to show you that again. We'll zoom in. So we want 92,000 on the graph. You can see we've got 80,000, okay, and it's going up in 4s. So that'll be 84. Then we get 88 as the second small square above. Now we go up to 92. So this is where we want to be in terms of, I'm going to try and highlight this on here. So I'm going to read across from the third square up, which is the 92,000. I'm going to read across the line. Okay, and then what I need to do is I then need to change that down. I then go down from that to reach my x-axis. So again, I've got a highlighter on here. Right, let's see, zoom in a little bit. I come down that line there until it reaches the x-axis. Okay, so my line's slightly wobbly. You should ideally do that with a ruler. But I think I've stayed on the right line. And now I need to read this value here. So you can see, hopefully here, that we're going from, I should underline the end a bit, is that we're going from 1,000 to 2,000. It's taking us approximately 10 squares to do that. So each small square is going to be 100. I can see that I'm the 6th small square along, which would take me up to 1,600 being my time in years. So if I zoom that back out, I'm ready to isolate the graph. I will have my answer as 1,600 years. 0 doesn't come out very well there. 1,600 years. And we've read that from the graph. So in terms of marking points, you get 1 mark for showing your work on the graph here. Okay, reading across from 92,000. Okay, you may want to show your work in there, but it's 1 mark for reading across from the graph as I've shown there. And a second mark is for doing the 1,600. Okay, you are allowed a bit of a range on this. So I just tell you what the range is, and I'll also put that onto the screen for you to see as well. So if you want to go over here now, you should be able to see the range. So you're allowed anywhere from 90,000 to 94,000 where you draw across, and you're also allowed anywhere between 1,500 to 1,700 years. And they would all get you 2 marks that question. Part B of the question says radium-226 was discovered by Marie Curie in 1898. The notebooks she used were contaminated with radium-226 and are still hazardous. He wants you to explain why the notebooks are still hazardous. So going back to our knowledge from the previous question, we found that the half-life of radium-226 was 1,600 years, which means that the radioactive isotopes will only halve, the total number that you have will only halve every 1,600 years. And you can see that it's only been just over 100 years since she used her notebooks when they got contaminated. So they've not even gone through one half-life yet. So therefore, they'll still be very radioactive. So you can see here the answer. So at the moment, in this year that I'm making the video, in 2021, only 123 years have passed since they were contaminated. Okay, as long as you've got around that figure, so only over 100 or 120 years have passed since they were contaminated. So half-life hasn't passed yet, so the activity will not have dropped by much. So the bit what you want to get across here, the idea that the activity won't have dropped by much, and it's not long ago in terms of the half-life time since they were contaminated. And remember, the half-life is 1,600 years, so that those notes that she made and got contaminated will continue to be highly radioactive for at least 1,000 years, if 1,600 years, if not for longer. Okay, so what we're moving on to next is part C, and it's a 6-mark question. And it wants you to explain how the properties of alpha, beta, and gamma radiation affect the level of the hazard at different distances. So let's get the key thing here. So he wants us to talk about distances and the level of hazards for alpha, beta, and gamma. So what we want to do is we want to take each one in turn, alpha, beta, and then gamma, and discuss the level of hazards at different distances. So you can see that I've added a note for alpha. The key thing is to get across the properties of alpha that they will then determine where it's most hazardous. So you can see here what I've written is that alpha is the most ionizing but least penetrating. So ionizing means it will turn atoms into ions and therefore is dangerous. And penetrating is how far it can travel. So alpha is the most ionizing but least penetrating, which means that alpha is the most hazardous at a short range. Because at a short range, the alpha particles could get to you, strike you, and therefore be very ionizing. But as we increase the distance from the alpha source, because alpha is not very penetrating, it won't travel that far. Okay, so that's what you need to summarize. And we need to apply this to beta and gamma. So if you haven't done very well on this question, you might want to pause the video now and use that framework to discuss beta and gamma. And then you can press play again and I'll go through them with you. So I've now put beta in there. So beta is the second most ionizing and the second most penetrating. It also has the second most range in air, which means that beta is most dangerous for medium ranges, so medium distances. Okay, it can't quite travel as far as gamma, so gamma is going to be most dangerous for far away distances and long distances, but it is more ionizing than gamma. So if you're at a point where beta can reach the person or individual or sample, then it's more likely to ionize it than gamma is, and therefore it becomes more dangerous. However, the further away you go, beta won't be able to penetrate that far or travel that far in air, therefore its danger will decrease. So to finish that question off then, I've put here that gamma is the least ionizing but the most penetrating. Gamma also has a large range in air, and that means that gamma is the most dangerous for long ranges. These questions tend to be quite difficult to mark, so you may want to just, having done a provisional marking of this question, you might want to ask your teacher just to double check that to see if it will get 6 marks or not. Okay, so we're on to the final question for this marked task, question 2. This is a detector and counter used in an experiment to show that a radioactive source gives out alpha and beta radiation only. 2 different types of absorber are placed one at a time between the detector and the source, For each absorber, a count is taken over 10 minutes and the average number of counts per second worked out. And the results are shown in the table. So you can see here that we've got no absorber used. We end up with 33 counts per minute. Whereas when we use card, we're getting 20 counts per minute, but when we use metal, 3mm thick, we get 2 counts per minute. It says, explain how these results show that alpha and beta radiation is being given out, but gamma radiation is not being given out. This question is worth 3 marks, and you can see we've got 3 different pieces of data. So we're going to have to use each of the 3 different pieces of data in order to be able to give us an account of why we've got alpha and beta but not gamma. Okay, so it's first of all important to sort of talk through what the different things are. So with the card, why is that an important addition to the experiment? What does that tell us? Well, the card, remember, is what stops alpha. So I've put here that the card stops alpha, but beta and gamma can pass through. Okay, so that's important because we can see if the count rate drops, which it does here, it goes from 33 to 20, which is a significant drop. We can see that in that case, that there should be some alpha radiation because it's now being stopped by the card. So with regards to the metal, what's that telling us? Well, metal will stop both alpha and beta, but it will not stop gamma. And the fact we've got a decrease here in the count rate again means that we're showing that that's stopping the beta particles from passing through. So the source must contain beta as a result. Why did it not stop gamma, or why is it showing no gamma is emitted? Even though we get a count rate of 2, we'd be assuming that the count rate of 2 is the background radiation for this experiment or in this room. So the fact that it's only at 2 means it's not above the background radiation, therefore there's no gamma radiation present from the source. So let's put this all into writing and explain how we get the marks in this question. Okay, so I've gone through and written my ideas about how you get the marks here. So the first one you can see is the card significantly reduces the count rate. Card stops alpha particles, but it doesn't stop beta particles or gamma rays. Proving the source contains alpha, because that's the only reason why you can explain the decrease here between the count rate with no absorber and the count rate with card. So it must contain alpha. However, the fact that it's still high, because it's still at 20 counts per second, which is a high count rate, then there must be another source present. So first mark for saying that the use of the card reducing the count rate proves the source must contain alpha. The second mark is for talking about the metal. So the metal significantly reduces the count rate. So metal absorbs alpha and beta particles, but they don't stop gamma rays. As the count rate is reduced, this means that beta must be present in the source. Okay, the final one is for saying why there's no gamma. So if gamma was present in the source, it would take much more than 3mm thickness of metal to reduce the count rate to 2. So if gamma was there, the count rate would not go down all the way down to 2 because it would require much more metal to reduce that. That's the third mark. So that's the end of that set of questions. I hope you found that useful. Thank you for listening.